So in the previous video, I talked about converting alkenes to alcohols using oxymercuration reduction, and that gave us the Markovnikov addition product. So now we're going to talk about converting alkenes to alcohols, where we get the alcohol added to the less substituted carbon of the alkene. So at this point, this is the third reaction we've seen that can convert alkenes into alcohols. First one we saw was an acid catalyzed hydration, and so we treat an alkene with water and a strong acid such as sulfuric acid. This gives us a carbocation, so it can rearrange to give us a product that looks like this. Second reaction we learned that converts alkenes to alcohols was the oxymercuration reduction. And so here we get the Markovnikov addition product similar to this one, but we cannot have carbocation rearrangements. And so we get addition of the alcohol to the more substituted carbon, but we do not generate a carbocation, so we cannot get a rearrangement. And now we're going to talk about hydroboration-oxidation. And so this converts alkenes into alcohols, where we get the anti-Markovnikov addition product, meaning that our nucleophile has added to the less substituted carbon. So notice, all three of these reactions convert alkenes to alcohols, but we get different products in all cases. These two, we could get the same product if there's no rearrangement possible, but for this particular molecule, you can see that we can obtain three different products. So as I said, we call this reaction a hydroboration-oxidation. And so in the first step, we do a hydroboration. For this, you're going to be either using BH3, so borane, THF complex. That's what this little dot means. It means that these two things are complex together. Or you're going to use B2H6 in THF as the solvent. So if I draw this complex out that I'm talking about, so boron here is attached to 3 hydrogens. And so notice that it does not have its octet filled. It only has 2, 4, 6 valence electrons. So it actually coordinates to the oxygen in THF. And so THF looks like this, where this is a 5-membered ring. And then the oxygen is able to share one of its electron pairs with the boron. So the boron acts as a Lewis acid, and this helps stabilize this boron, because without this, it is highly reactive and we're not able to use it or buy it in a bottle. And then after the hydroboration step, we then have to do oxidation to get to the alcohol. So our oxygen comes from this step here. And for the second step, you're always going to use hydrogen peroxide, so H2O2, with sodium hydroxide and water. So as with everything else, we need to consider stereochemistry if we have sp3 hybridized carbons. In this case, stereochemistry of these type of reactions, if we produce a chiral center, it's going to be stereospecific. That means we must get a particular product based on the reagents that we used. Notice that we have to get the hydrogen and the OH that is added to the alkene on the same side of the molecule. And so these are what's called syn addition. So we've talked about anti-addition in previous reactions. In this case, we get syn addition, where the H and OH add to the same side, and this must happen because of the reaction mechanism. Also notice the regiochemistry of this reaction. Where does the hydrogen add to? Does it add to this carbon or this carbon? And where does the OH add to? Does it add to this carbon or this carbon? Notice in both of these cases that I drew, the hydrogen atom adds to the more substituted carbon, and the oxygen, the OH, adds to the less substituted carbon. So there's two reasons why we get this type of regiochemistry, where the OH adds to the less substituted carbon and the hydrogen adds to the more substituted carbon. First reason is hydrogen is more electronegative than boron, and so if we draw out the BH3 molecule and we look at an electronegativity table, we see that hydrogen has an electronegativity value of about 2.2, and boron has an electronegativity value of about 2.0. And so although it's not very big difference, the boron does have a partial positive charge on it. Remember in our previous mechanisms, like when we've used HBr, the partial positive is on the hydrogen, and we attack that hydrogen first. In this case, the partial positive is on the boron, and so that's what our alkene is going to be attacking in our mechanism that we'll talk about in just a second. Second reason is steric hindrance. Boron is quite a bit bigger than hydrogen, and so when it comes in to add to the alkene, it wants to sit over top of the carbon that is less substituted so that it doesn't bump into larger groups. So let's take a look at the mechanism of this reaction. So sticking with the theme of this chapter, we're going to be going through a cyclic transition state to form our intermediates. In this case, though, it's going to be a 4-membered type of ring instead of 3-membered ring. And in addition to that, this mechanism is quite long, so just be prepared for that. So we take BH3 and THF. Remember, this is a complex, but THF doesn't really play a role in our mechanism. It's just the borane that does. So if we draw out BH3, and remember the partial positive is on our boron. And so our electron-rich alkene is going to attack the boron. And then the boron does not have a lone pair, but these bonds between the boron and hydrogen are nucleophilic and can come back in and attack the alkene. So if you draw out the transition state for this with dotted lines, you're going to see that we have a 4-membered ring transition state. So remember, this double bond is breaking, so we draw a dotted line. This hydrogen carbon bond, sorry, I drew these arrows wrong. This hydrogen should be adding to the more substituted carbon here, and so we would be forming a bond between this hydrogen and this carbon. This hydrogen is breaking a bond with the boron that's still attached to the other 2 hydrogens. And then this boron is making a bond to this carbon. And so all of this is happening at the same time. And notice this is a cyclic transition state in a 4-membered type of ring. And so if we get rid of that transition state, we follow our arrows through here, we get, this is an electrophilic addition mechanism, and our alkene, let's see here, so we add the hydrogen and the boron to the same side. So we're going to get hydrogen addition here. I'm just going to draw it facing down. You could draw it facing up if you wanted to. And then our boron that is added is also facing down. And so we take our molecule that we generated here, our alkyl borane compound, and then notice we had BH3, and now we have BH2 attached to some carbon stuff. This BH2 can further react to substitute out these 2 hydrogens with other alkyl groups. And so if we go through the rest of the mechanism, we're going to add some more of these carbon groups. But let's first think about the best way to think about this reaction step, even though it's not the correct mechanism. I think the best way to think about it is in a 2-step type of process, even though this is the actual mechanism and it's concerted, meaning that it happens all in one step, getting us to this point. But if you want to think about it like this, we take our alkene. So I'll just draw out this alkene here, same one we had over here. And again, remember that our boron is partially positive and our hydrogens are partially negative. So you can think about it as going electron rich to electron poor. And then we kick out H- as our leaving group. We want to put the positive charge on the most substituted carbon, as we usually do. And so that positive charge is going to be most stable here, where our BH2 has added down here. The H minus that we kicked off could then come back and do a coordination type of step to get us to something that looks like this. Notice in this type of mechanism, a carbocation is flat, and so we would expect the hydrogen to attack from both the top and the back, giving us a mixture of products at this position. That is not the case. We know that we add hydrogen and boron to the same face of the molecule, and so it must be this type of mechanism where it's concerted and it all adds at the same time. I think this over here, though, is just a good way to think about how the mechanism proceeds. So if we go back to the actual mechanism, this occurs to get us to here. This can occur again with another alkene, so let's draw that out here. I'm going to draw it flipped around so that we can show it reacting with this boron species. We go electron rich to electron poor, and at the same time this hydrogen comes back in and makes a bond. And so after this step we get to an intermediate that would look like this. And so we would now have the addition of two of these cyclohexane type of molecules to our boron. And now, again, our boron has one more hydrogen bond, so it can do this again. So we have another alkene floating around, our alkene electron rich to the electron poor boron, and then the hydrogen adds to the more substituted carbon, getting us to an intermediate that looks like this. So we have our boron, let's see here, attached to this, and attached to this, and now it's attached to a third one as well. So we would get a species that looks like this. So the hydroboration, the first step, we add one of our alkene containing groups to the boron, then we add a second one, and then we add a third one. This one down here, these are alkyl groups, remember? And so we call this a trialkyl borane. It is then this trialkyl borane that goes on to participate in the oxidation step. All right, so I've redrawn out our trialkyl borate over here. I'm only going to draw out one of these alkyl groups, and I put R to represent the other two, so I don't have to draw them out the entire time. So that's the end of step one. Step two, we are going to do the oxidation part to get our alcohol onto the molecule. When we mix these three things together, there is an equilibrium between the hydrogen peroxide and the sodium hydroxide, where the hydroxide is able to deprotonate the peroxide, giving us a molecule that looks like this. So we made water via this proton transfer reaction, and we have a negative charge on our peroxide oxygen. So at this point, remember our boron only has 6 electrons, and it would like to fill its octet, and so this extra pair of electrons can come in and attack our boron. So our oxygen has a negative charge since it has 3 lone pairs, and then we get a coordination step. So we go through coordination, and that gets us to something that looks like this shown here. And so boron, even though it's lacking an octet here, it's neutral if you do the formal charge calculation. And then here we've given it a pair of electrons, and so there is a negative charge on the boron. All right, so at this case, boron would prefer to be neutral, and so we get a 1,2 alkyl shift. So get rid of this up here, 1,2 alkyl shift. So essentially this carbon-boron bond is going to shift over to our oxygen, and we're going to kick out hydroxide. And so again, this is a 1,2 alkyl shift. Our alkyl group has gone 1, 2 from the boron to the oxygen. If we draw out what this gives us, we get to an intermediate that looks like this one shown here. And so if we follow our arrows through, this arrow is indicating that the carbon-boron bond is breaking. A new carbon-oxygen bond is forming, and then the oxygen-oxygen bond is broken. Remember, oxygen-oxygen single bonds are fairly weak, and so this is going to easily break. And this now gets us to this point. Notice that we keep the same stereochemistry because of the constraints of the molecule. Whenever this shifts over, the oxygen must assume the same position as the boron. So boron is pointing down, oxygen is now pointing down. Also, just like before when we had BH3, we substituted out all 3 of the hydrogens for alkyl groups, we can have this same mechanism occur twice more with these other R groups on here to essentially insert an oxygen between the boron-carbon bond. So after that happens twice more, we get to a molecule that looks like this, where an oxygen has essentially been put in place in between the boron-carbon bond. Remember, this happens because of the 1,2 alkyl shift, and we call this type of compound a trialkyl borate ester. And so once we form this in our reaction mechanism, we then are going to have coordination of hydroxide. So we draw out our hydroxide here. Has a negative charge because it has 3 lone pairs, and we get a coordination to take place. So this would be coordination, and that gets us to something that looks like this. So notice I represented 2 of these groups with R's. I only drew out 1, so I don't have to draw them all out. We gave electrons to our boron, and so now it has a negative formal charge. And so at this point, our boron wants to go back to being neutral, and so we have a heterolysis step where this oxygen takes electrons with it. So we went from boron having 6 valence electrons to 8. Now we take 2 away and we go back to having 6. Once this happens, we're concerned with our organic molecule, and so we have this intermediate shown here after this heterolysis step. And now we have an alkoxide, which means a negative charge on an oxygen. And at this point, we have a proton transfer from our water in our reaction. To give us our final molecule. So this last step was a proton transfer, and this gets us to here. Notice once the boron left at this point, we still have 2 other alkyl groups that are on there, and so this can happen twice more to produce three of these molecules plus a byproduct that looks like this, where hydroxide has added 4 possible times to the boron. So I know this was a long mechanism, but this is an extremely useful reaction in organic chemistry. So I know you'll see it again. And so just remember, when you treat alkenes with a boron reagent, such as borane THF, followed by oxidation, so hydrogen peroxide, sodium hydroxide, you get addition of the OH to the less substituted carbon, and the OH and the H add to the same face of the molecule. So with all the other reactions we've been looking at, again, we can do similar reactions with alkynes that we can do with alkenes. So we can take terminal alkynes, use hydroboration-oxidation to convert them into aldehydes. So this is the first time we've seen the synthesis of an aldehyde. And then if we take internal alkynes, we would get ketones. This isn't the best reaction though, because you're going to get mixtures of regioisomers if it's not a symmetrical alkyne, and so it's better to use like oxymercuration for this type of conversion. But this is a good way to convert terminal alkynes to aldehydes. We're going to have to use a bulky dialkyl borane, which I'll talk about in just a second. And that's because if we use BH3 coordinated to THF, like we just saw with alkenes, we're going to get a mixture of products, and this is not very useful. So you can see after BH3 reacts with our alkyne, we get an intermediate that looks like this. And again, we have a pi bond that can further react with this type of species. And so we're going to get addition of our nucleophile to both of these carbons, or multiple additions. And so this is not useful. So for conversion of terminal alkynes to aldehydes, we need to use a bulky dialkyl borane. So remember in the previous mechanism when we did this with alkenes, we substituted all 3 hydrogens on the boron atom for alkyl groups. And so if we go ahead and substitute 2 of those hydrogens for alkyl groups, we can only react 1 of those boron hydrogen bonds. On top of that, if we use big bulky things, this is going to force the boron to add to the less substituted carbon, giving us the anti-Markovnikov addition product, resulting in the aldehyde. 2 common bulky dialkyl boranes that you'll encounter is disamal borane, shown here, and 9-boro-bicyclo-331 nonane. You don't need to remember this name. We can just call it 9-BBN, and it looks like this. So let's take a look at the mechanism shown here, converting terminal alkynes to aldehydes. So I have 9-BBN written up here. Remember that 9-BBN looks something like this. And so this gives us a bulky dialkyl borane. We have the same type of mechanism we had earlier where our electron-rich pi bond attacks the electron-poor boron. And then we have the hydrogen atom add back into this pi bond. This gets us to an intermediate that looks like where the hydrogen is added here. And then our boron species has added here. Let's see here. That's not right. There we go, something like that. And our boron has gone from, let's see here, from having 3 bonds to 3 bonds, so there's no charge on there. And then at this point, since we can't add any more alkyl groups to this boron, it's already a trialkyl borate, we move on to step 2. Just like before, our sodium hydroxide can deprotonate the hydrogen peroxide, and so we get a species that looks like this, and this can do a coordination to our boron atom to give us a intermediate that looks like, let's see here. I'm just going to put R on our boron to simplify drawing this molecule, which would be fine for you to do on an exam as well. And then this coordination gives us a species that looks like this. Remember, our boron now has a negative charge on it. And at this case, at this point, just like we saw before, we get a 1,2 alkyl shift where our carbon that is attached to the boron shifts over to the oxygen and then kicks out hydroxide. This gets us to an intermediate that then looks like this shown here. So remember, our stereochemistry is maintained. Our boron added to the same side as the hydrogen, and so the oxygen is going to be on the same side as the boron. So we get to an intermediate that looks like this one shown here. All right, so just like in the previous mechanism, we now have hydroxide do a coordination step to the boron. So we get a mechanism that looks like that. We've given a pair of electrons to boron, so it has a negative charge, and it wants to go back to being neutral. So we get a heterolysis step, giving these electrons to the oxygen. That gets us to a species that looks like this, shown here. And now at this point, we have water do a proton transfer to give us our final neutral organic molecule. So proton transfer to get us to here. Remember that this is an enol, so we have an alkene attached to an alcohol, and this rapidly tautomerizes into the aldehyde. So just like I talked about at the end of the previous video, when you're on the exam, you're going to see multi-step reactions now that we've learned several different ones. In the previous video, I went in the forward sense. I started with a molecule and did reaction after reaction to get to a final product. I might also ask you to think backwards. So in this case, we want to make this aldehyde. What would we need to have for this single reaction? And then what could we make compound B from to get compound A? So you want to take this one step at a time. We see that we have an aldehyde. And to get there, we treated some molecule, molecule B, with 9-BBN, followed by hydrogen peroxide, sodium hydroxide, and water. We know that this is a hydroboration-oxidation. We know that 9-BBN is a bulky dialkyl borane, typically used to convert terminal alkynes into aldehydes. So if we think about that, we want to draw a terminal alkyne here. Count your carbons, 1, 2, 3, 4. We're only going to have 4 carbons here. And so if we draw a terminal alkyne, it's going to look like this. Again, 1, 2, 3, 4. Terminal alkyne treated with this would get us to the aldehyde. All right, so now we know that molecule B is this terminal alkyne. And then again, we want to get to compound A. We see that we treat compound A, whatever that might be, with excess sodium hydride. We know that excess sodium hydride means sodium hydride acts as a base, and so we're going to be doing elimination reactions. We know that elimination reactions can make pi bonds, and we know if we have excess, we're probably doing more than one elimination reaction. We also see that we have an acid workup step, and so this would be consistent with forming a terminal alkyne. How do we form terminal alkynes? Using excess sodium hydride. We typically do that using either vicinal dihalides or geminal dihalides. I'll just draw out a vicinal dihalide in this case. Again, we had 4 carbons. We have 4 carbons here. And I could have drawn out any type of leaving group. It could be chlorine, bromine, tosylate, any type of good leaving group here would be eliminated once to give a vinyl halide, eliminated twice to give an alkyne, and then acid workup to protonate this. So this could be a potential molecule A, and this would be molecule B. Again, when you get to these molecules and you want to double check yourself, think about it in the forward sense. If I take this molecule and treat it with excess sodium hydride, what do I get? I get an alkyne that's deprotonated, and I need to reprotonate that with an acid workup. That gets me to here. That makes sense. Now that I'm here, I treat that with 9 bbn. I know it's a bulky dialkyl borane, and so that is going to give me hydroboration, where the boron is on the less substituted carbon. And then we oxidize that to an OH using these conditions here. Ultimately, that gets me to an enol, which tautomerizes to the aldehyde. And so all of this would make sense.